Right, and next exercise 16. So we are given an odd integer a here. We have to prove that this is divisible by 12. Solution: since a is odd, a will be of this form: 2k plus 1 for some integer k. K may be negative also, because we are given only the fact that a is an odd integer. A itself may be negative, that's why. So we cannot assume here that k is a positive integer, it's some integer. Then, so we straight away use this expression here. So a square plus a plus 2 whole square plus a plus 4 whole square plus 1 now becomes 2k plus 1 whole square plus 2k plus 3 whole square plus 2k plus 5 whole square plus 1. So now we expand these powers. 4k square plus 4k plus 1 plus 4k square plus 2 times 2 times 3 is 12 plus 3 square is 9. Then this one 4k square plus 2 times 2 times 5 is 20 plus 25 plus 1. So 3 4k squares give us 12k square plus, now we look at the k's. 12 plus 4 is 16, 16 plus 20 is 36k plus, now the constant terms. 1 plus 9 is 10, 26 plus 10 is 36. So clearly this is divisible by 12 because all the terms are divisible by 12. So that's the solution. Then 17. Sometimes it is this straightforward, it won't be always the case. Prove that the expression three n factorial divided by the nth power of 3 factorial. This expression is an integer for all non-negative integers n. And this we will prove by induction. we apply induction on n. When n is 0, this expression becomes what? 0 factorial divided by 3 factorial means 6. So this is 1. So that means when n is 0, our claim is true, it is an integer. Assume that this is an integer for some non-negative integer n. We now try to show that not the same expression but the one where n is replaced by n plus 1, that is also an integer. So that will be our induction step. Now so we should carefully replace n with n plus 1. Wherever n is appearing, we should write n plus 1 in those places. To the power n plus 1. This is equal to, so you can see that this becomes the factorial of 3n plus 3. And in the denominator you have 3 factorial to the power n times 3 factorial, which is 6. Okay, so now this becomes equal to, I need ink. Three n plus 3 factorial can be written like this. 3n plus 3 times, okay, this is not prominent. Three n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial divided by this. So that becomes equal to what? So you can see that what are we having here? 3n plus 1 times 3n plus 2 divided by, so you see that you can take 3 common out from this 3n plus 3, so that will leave you with n plus 1 in the numerator and in the denominator you will have 2, because that 3 will there will be a cancellation with 6 times 3n factorial divided by 3 factorial to the power n. Now this part is an integer. Do you see why? It's because 3n, we have a product of two consecutive integers, 3n plus 1 and 3n plus 2. So if n is even, then 3n plus 2 is also even, so that is divisible by 2. If n is odd, then 3n plus 1 is even, and that is divisible by 2. So this is going to be an integer, and this is an integer by our induction hypothesis. So we put a semicolon here, since three n plus 1 times 3n plus 2 is even, and by the induction hypothesis, this is an integer, we conclude that this is an integer. This completes the induction. So this one is also quite straightforward. Next we see 18. Prove. Here we have to prove 3 statements. The product of any 3 consecutive integers is divisible by 6. Like that, the product of any 4 consecutive integers is divisible by 24, and finally the product of any 5 consecutive integers is divisible by 120. And I think there is a hint also given here. Hint. What is the hint? The corollary 2 to theorem 2 4. See what we will do is we will try to see the connection between these 3 statements, and we will prove only one of them, namely say the middle one. Okay, the product of any 4 consecutive integers is divisible by 24, and the other 2 can be similarly proved. You will understand why that is so. So let us start the solution. We only prove that the product of any 4 consecutive integers is divisible by 24. Oh, so I want to prove the middle one. Shall I need the first one in this proof? That's what I am thinking. We will need the first one. Okay. So what? Okay. So instead of going like this, we prove the first 2 and the last can be similarly proved. We only prove the first 2 statements. The third can be similarly proved. Okay, so that means we start by taking any integer. Let a be any integer. Okay, and this a may be negative also, it may be positive, negative, it can even be 0. By the division algorithm, there, okay, I don't have to write exactly what the algorithm says or what that result says, but I want the consequence. By the division algorithm, A is of one of the forms 3k, 3k plus 1 and 3k plus 2, where k is an integer. Now what we want to prove here is that this product is divisible by 6, because a has been chosen to be an arbitrary integer, so this is a product of any 3 consecutive integers. Okay. So we look at the cases. If a is equal to 3k, then a times a plus 1 times a plus 2 is equal to 3k times 3k plus 1 times 3k plus 2, which is divisible by 3, of course, because we have 3 here. If a is equal to 3k plus 1, then what happens to this product? This becomes 3k plus 1 times 3k plus 2 times 3k plus 3. This factor is a multiple of 3, so that means again this is divisible by 3. And finally, if a is equal to 3k plus 2, then this product becomes 3k. This 3 is looking like a gnarled 3. 3k plus 2 times 3k plus 3 times 3k plus 4. Again, here the middle one is divisible by 3. Hence, in any case, 3 divides this product. Now our next observation is that this product is also, besides being divisible by 3, is also divisible by 2. Why? Because, for example, a times a plus 1 is always even. This we have seen many times by now. If a is even, then of course a times a plus 1 is even. If a is odd, then a plus 1 is even. So in any case, this is divisible by 2, so its multiple, this multiple is also divisible by 2. Now, since the greatest common divisor of 2 and 3 is 1, so here we use that what is given in the hint, corollary to theorem 2-4. We have by corollary to theorem 2-4 the fact that the product of these two divisors, that is 6, it also divides this. Okay, so that's how we have proved the fact that 6 divides the product of any 3 consecutive integers. Next, we prove that 24 divides this. In a product of any 4 consecutive integers. A was originally chosen to be any integer, so we can use that A here. Okay, now how can this be shown? You have seen the first statement being proved. So what we did is that we proved that the given product is divisible by 2 numbers whose product is our required divisor. But at the same time, those 2 numbers are relatively prime. So something like that can be thought of here also. So 24 is 8 times 3, right? Now note that in this product of 4 consecutive integers, a part of it is already a product of 3 consecutive integers, a times a plus 1 times a plus 2, or if you want, you can think of this one also, a plus 1 times a plus 2 times a plus 3. That is also a product of 3 consecutive integers. So by what we have proved above, this part, 3 already divides this thing. Now what we have to prove is that 8 divides this. So let us first mention that 3 thing, since a times a plus 1 times a plus 2 is a product of three consecutive integers So that means by what we have already proved above, 3 divides this product of 4 consecutive integers. And hence 3 divides this. Now we should concentrate on showing that 8 divides this product. Note that the product is already divisible by 4. How? It has these two parts, a times a plus 1, which is always even, and it also has this part, a plus 2 times a plus 3. These are products of 2 consecutive integers, and so each one of them is divisible by 2, and since both of them are separately available in this entire product, so the entire product is divisible by 4. But how is it divisible by 8? So we have to think of that. Because if we use that argument, we only get the fact that 4 divides this thing, but that's not what we want. We want 8. Okay, there is of course one very direct method. You don't have to think of anything, you just look at all the numbers of this form, 8k plus 1, 8k plus 2. By the division algorithm, a will be of one of these forms. Then you just look at all these cases separately, but it takes a lot of calculations, or at least you have to write all the cases down. So I'm thinking if that can be somehow compressed. Okay, what do these products look like? A square plus a. This one, however, is a square plus 5a plus 6. No, that has nothing to do with 8. What if we take a and a plus 3? Let me just see for a while if something can be done to uh, reduce the amount of calculation. A square plus 3a, if we multiply this and this, and if we take the product of the middle ones, then we get a square plus 3a plus 2. Oh, okay. So a square plus 3a and a square plus 3a, have I done it correctly? A square plus 3a, okay, and a square plus 2a plus a is 3a plus 2. Now we know that any square number is of the form 4k or 4k plus 1. It is of the form 4k when the number itself is even, and when the number is odd, then it's of the form 4k plus 1. Oh, so I think we can reduce our work by just simply considering a to be even or odd. That will also amount to us doing some calculation. We have to do something. We cannot avoid everything and conclude the final thing. Okay, so let us just see that itself. What happens when a is even and what happens when a is odd? I am not ready to write the solution yet. Let me just first roughly see if we get to some place. If a is even, then what happens? 2k times 2k plus 1 times 2k plus 2 times 2k. Okay, so this is actually not giving me anything, because from here, just like before, we are getting 1 2 from here, another 2 from here, only 4, because these two are odd, and then again we have to think about them. So if 2 is not the thing, then let us try 4. Yeah, if we take 4, then a has these 4 forms. A is either of the form 4k or 4k plus 1 or 4k plus 2 or 4k plus 3. So if a is of the form, yeah, I think that will work. Now a is of one of the forms 4k, 4k plus 1, 4k plus 2, 4k plus 3. Okay, where k is an integer. So let us start. If a is 4k, then times a plus 3 will be what? 4k times 4k plus 1 times 4k plus 2 times 4k plus 3. 2 will come out from here. Combining that with this 4, we are getting 8. So instead of saying those things, we just simply write, which is divisible by 8. If a is of the form 4k plus 1, then this will be equal to I think there is some shorter way of proving that 8 divides this product. Right now it's not coming to me. You can try to find. So now this becomes 4k plus 1 times 4k plus 2 times 4k plus 3 times 4k plus 4. So you see that now this factor gives us 2 and this last factor gives us 4. Again we are getting 8. Then if A is of the form 4k plus 2, then our product is 4k plus 2 times 4k plus 3 times 4k plus 4 times 4k plus 5. So this one gives us 2, this one gives us 4, 8 again. And finally, if A is of this form, then this is equal to 4k plus 3, 4k plus 4, 4k plus 5 and 4k plus 6. And this time this gives us 4 and this gives us 2. Which is divisible by 8. So in any case 8 divides this product of 4 consecutive integers. Combining this with the relation that 3 also divides this product, we get our result. To theorem 2 for since let us mention that also, that the divisors 3 and 8 are relatively prime. 24 divides this. And the one that we are leaving, we said we will not solve, is the one where we take the product of any 5 consecutive integers. And what is the divisor? 120. Now 120 is 5 times 24. Yes. So 24 already divides this. So that means 24 will also divide this. So you just have to prove that 5 divides this. And that is quite easy. I mean, I think the middle one is the somewhat problematic one. Why I am saying that is because here the number by which we are dividing this product, that is only a prime number, 5. So you just consider those 5 cases. You can see that this third one, I mean, you can almost see that it's already done. If A is of this form, then of course this is divisible by 5. If it is 5k plus 1, then A plus 4 is 5k plus 5, that is divisible by 5. If it is of the form 5k plus 3a, then 5k plus 2, then a plus 3 is 5k plus 5. If it is 5k plus 3, then a plus 2 is 5k plus 5. And if it is 5k plus 4, then a plus 1 is 5k plus 5. So in any case, this is always divisible by 5. And that's just it. Then you apply this corollary, because 5 and 24 are relatively prime, their GCD is 1. So by that corollary, 120 divides this. That's just it. So we conclude the solution here, incomplete solution. Incomplete in the sense that we are not including these writings in our solution, only that much. Everything else we have shown. So this was our 18. Now 19. Exercise 19 has many parts. And it is here also we are going to see divisibility. Establish each of the following assertions below. Part A. If A is an arbitrary integer, then 6 divides a times a square plus 11. Part B. If a is an odd integer, then 24 divides a times a square minus 1, and a hint is also given for this one. The square of an odd integer is of the form 8k plus 1, which is a fact that you either know or it can be proved quite easily. Then if a and b are odd integers, then 8 divides a square minus b square. Then if a is an integer not divisible by 2 or 3, okay, then (24) divides a square plus 23, and finally part E, if a is an arbitrary integer then 360 divides a square times a square minus 1 times a square minus 4. Okay, let us now see how we can solve each one of them. So for part A is any integer. And what do we have to show? We have to show that 6 divides this, since 6 divides 12, it's enough to show that 6 divides a times a square minus 1. Do you see why? a times a square plus 11 can be written like this: a times a square minus 1 plus 12, and if you combine that with, multiply that with a, then you get this. That means here what do we have? A cube plus 11a. In its place what we have written is a cube minus a plus 12a. So this is divisible by 6 if and only if this is divisible by 6, because this one is already divisible by 6. So that's why it's enough to show that this is divisible by 6. Since a times a square minus 1 can also be written like this: a minus 1 times a plus 1, this is a product of 3 consecutive integers. So it is divisible by 6 by the previous exercise, and in fact we don't have to do anything here. So by the previous exercise, six divides this, and that's just it. Then part B, if a is an odd integer, then 24 divides this. Okay. Note that the integer that we have here is actually what we have, what we had to consider here, and that is already divisible by 6. Oh, but we cannot work with 6 and 4 because they are not relatively prime. So that is divisible by 3. This is something we already know. Divisible by 6 means automatically it's also divisible by 3. What we now show is that this is also divisible by 8. Oh, and there this fact will be useful, that the square of an odd integer is of the form 8k plus 1. We can in fact start like this: by the solution to part A, 3 divides this because 6 divides this. Since A is odd, A square is of the form 8k plus 1 for some integer k. In fact, because a square is non-negative, so k here has to be non-negative. A square is not just non-negative. Because of this form, a square in fact is positive. So k has to be a non-negative integer, but we don't need that fact here anywhere, so that's why we are just simply mentioning for some integer k. Then a square minus 1 is 8k, hence 8 divides a square minus 1, and that is why it also divides this. So by corollary 2, the theorem 2,4 24 divides this. Not that we are no longer writing that since the GCD of 8 and 3 is 1, so we are able to apply this corollary. We haven't written that fact, that is understood. Similarly, the use of this corollary in concluding such divisibility relations will also not be mentioned. I mean, the further we go inside number theory, the less such actual references will appear. Okay, so this is just it. Now we move to part C. If A and B are, or this is very easy, you just use this one. Since A comma B are odd, A is of A square, I should not forget that the square is of that form, is 8k1 plus 1, and B square is 8k2 plus 1. For some integers k1 and k2. Thus, a square minus b square is 8 times k1 minus k2, which is, let's just write that also, which is divisible by 8, and that's what we wanted to show. Next, part D. In part D we have to prove that if A is an integer not divisible by 2 or 3, then 24 divides A square plus 23. Looking at what we did here, you can imagine that there 20 in place of 23 we can write 24 minus 1, so 24 can be forgotten, leaving us with a square minus 1. So we would then try to show that 24 divides a square minus 1. Since, or we can just simply write like this, it's enough to show that 24 divides a square minus 1. Okay. Oh, now we don't have that facility of a product of 3 consecutive integers because a is missing. But we have to use that fact that a is neither divisible by 2 nor divisible by 3. So how can we use that fact? At least we know one thing. You see, because a is not divisible by 2, so a is odd. So a square is of the form 8k plus 1, and that is why 8 divides a square minus 1. Since 2 does not divide a is odd. Hence a square is equal to 8k plus 1 for some integer k, which implies 8 divides a square minus 1. Now what else is given to us? A is also not divisible by 3, since 3 does not divide a is of the form, we have taken k once, we can take k here also, 3k plus 1, 3k plus 2, because k is just some integer, it plays no other role, but still for the sake of making it different from this one, let us take say n, or 3n plus 2 for some integer n. If a is 3n plus 1, then what is a square minus 1? (9n square plus 6n) plus 1 minus 1, so they cancel each other, which is divisible by 3. And what happens in the other possible case? We have only one other case. If a is 3n plus 2, then a square minus 1 is this, which is 9n square plus 2 times 2 is 4, 4 times 3 is 12. plus 2 square is 4, 4 minus 1 will be 3. Which is also divisible by 3. So in any case 3 divides a square minus 1. So 8 also divides a square minus 1. So by corollary 2 to theorem 2, 4, which we are no longer going to write. We understand what we are doing here. Thus, that corollary says that 24 divides a square minus 1, and hence 24 also divides a square plus 23. So that is D, and there is one more, E. Here what we have to, I wrapped that up, we have to prove this a square times a square minus 1 times a square minus 4 for any integer a. This time a is again an arbitrary integer, there is no restriction on a, and 360 Okay, so what happens when we 40 times 9 is 316? Note that, so let us start like this. What we now try to do, we aim to show that this integer is divisible by 40 and by 9. And note that 40 and 9 are relatively prime, because the only prime factor of 9 is 3, and that is not available here in the factorization of 40. So they are relatively prime. So we start by noting this. Note that a square times a square minus 1 times a square minus 4 can be written like this. A times a square minus 4 is a plus 2 times a minus 2. That a minus 2 we take here. From a square minus 1 we will get an a minus 1. And from this a square, one a we have kept outside and the other we are writing here. Like a minus 1, we also get a plus 1 from here and a plus 2 from here. So you see that this is the product of 5 consecutive integers. Since by the previous, it was the previous exercise, now let me just see, I am forget, yes, by the previous exercise (120) divides a product of 5 consecutive integers. We conclude at once that 40 divides this. Exactly how? 40 divides 120, so 40 divides this thing, so 40 divides this thing times a, that means this. So that's how we are getting this final conclusion. Now our next aim is to prove that this integer is divisible by 9, and in that we are going to use the three forms in which we can find an integer, that is 3k or 3k plus 1 or 3k plus 2. We won't even mention that fact, we will just simply start writing the cases because that's something that is well known and extremely elementary in number theory. I need ink again. Next, if a is equal to 3k, where it's also understood that k is an integer, okay, those things won't be repeated again and again, then a square times a square minus 1 times a square minus 4 is 9k square times this times this, which is divisible by 9. If a is of the form 3k plus 1, then this is 3k plus 1 whole square times whole square minus 1 times minus 4. We keep the first factor as it is because it's not going to give us anything. We expand this one. This becomes 9k square plus 6k plus 1 minus 1 will be 0, and here we will get 9k square plus 6k plus 1 minus 4 means minus 3, and this ultimately gives us what? 3k plus 1 whole square. We can take 3 common out, and here also, from here also we can take 3 common out, so that means we will get a 9 outside, and here inside we will be left with 3k square. If you want, you can take k also common out, but that does not serve any purpose, so we are keeping the k's inside. 3k square plus 2k, and here 3k square plus 2k minus 1, okay, which is again divisible by 9. And there is one more case. If a is 3k plus 2, then like before, this is not going to give us anything. So we don't bother to expand it or do anything to it. Here, however, 9k square plus 12, 2 times 2 times 3 plus 4 minus 1, that means 3 times, like that. Here 9k square plus 12k, oh, here 4 and minus 4 will cancel each other, and now what will this become? So we can take 3 common out. Here also we can do that. So we have 9 outside. 3k square plus this, like that, in that other factor, which is again divisible by 9. So in any case, nine divides this product, hence by corollary 2 to theorem 2,4, and that is applicable because 9 and 40 are relatively prime. We decide to at least show what we have done here, that is 360 divides this, so that completes the solution in its entirety. Next, exercise 20. Just like 19, this one also has quite a few parts. Confirm the following properties of the greatest common divisor. And here all the parts are somewhat theoretical, they don't involve concrete numbers. Let us see the parts. If the greatest common divisor of A and B is 1 and the GCD of A and C is also 1, then the GCD of A and BC is also 1, and hint is given for this one, which actually is the entire solution. So much has been given that we don't have to really do anything. Because one is equal to ax plus by, that is equal to au plus cv for some integers x, y, u and v. So this and these things happen. Where are we getting these conditions from? We are getting them from these two given conditions. A and B are relatively prime, so some linear combination of them will be equal to 1, where the coefficients x and y are integers. This is something we already know. Just like that, this one also gives another such condition. For some x, y, u, v, and here the author of course means that these x, y, u, v, these are integers. It has not been mentioned explicitly because we are dealing only with integers so far. For some this, so this thing happens, 1 is equal to ax plus by times au plus cv. Don't mess this up when you write these things. A and B are there in one condition and A and C are there, not B and C. Now if one multiplies the terms out, one gets this: A times aux plus cv, I mean you can see it easily, plus cvx plus byu. These are the terms that will have a in them, and the term obtained by multiplying these two, that does not have a, it has bc. Okay, so that is the hint. This hint is almost the entire solution. We just have to write the final conclusion after this. Anyway, let us see part B then. In part B, if the GCD of A and B is 1 and C divides A, then the GCD of B and C is also equal to 1. Then part C, if the GCD of A and B is 1, then the GCD of, I have to break this up, AC and B equals the GCD of C and B. So we got rid of A entirely. And here these two GCDs are equal, they are not necessarily 1. Okay. Part D. If the GCD of A and B is 1 and C divides the sum A plus B, then the GCD of A and C is equal to the GCD of B and C, and both of them are equal to 1. And a hint is given here. Let D be defined to be the GCD of A and C. Then D divides A and D divides C, and this implies that D divides A plus B minus A, or D divides B. Some such things have to be done. Now there are two more parts. Shall I be able to squeeze them here? E. If the GCD of A and B is equal to 1, D divides AC and D divides, okay, what am I, have I written it correctly? And D divides BC also, yes. Then D divides C, and finally if the GCD of A and B is equal to 1, then the GCD of A square and B square is also equal to 1. We have been able to complete it barely. Okay, so now let us start the solution. First we have to prove this, that and here almost everything is done already. So let us take advantage of what we have written there. We will use this space, but let us start the solution somewhat here. Since A and B are relatively prime and A and C are also relatively prime, we have we have this and this for some integers, this. Let us continue like this. So 1 has been written like this. Now note that this final expression is a linear combination of a and bc, and the coefficients, this one and yv, are both integers. Why? Because whatever we have, whatever we see here, all the symbols are integers. So this aux plus cvx plus byu, this is an integer, and yv is also an integer. We will recall the parts when we need them, okay? Now, if D is the GCD of A and BC, then D divides A and D divides BC, because greatest common divisor means it divides both the numbers, and that is why D divides this also, because we have A here and in this second term we have BC here. And this is equal to 1, I mean this expression. But then D is equal to 1, because the GCD by definition is a positive integer. So there is only one positive integer that divides 1, namely 1 itself. So this is the only possibility, that is this is equal to 1. So this is part A. In part B, we are given this. And C divides A. We have to prove this, that GCD of B and C is also equal to 1. Suppose D, which is the GCD of B and C, is greater than 1. There are only two possibilities, either D is equal to 1 or it is greater than 1. No possibility of having it less than 1. So suppose this is greater than 1. Then D divides B and D divides C, because D is their GCD, and C divides A. Since C divides A, we have D divides C and C divides A, they imply D divides A because the divisibility, that relation is transitive. Okay, so we are having this, hence D divides both A and B, so it will divide their greatest common divisor, which is equal to 1. Thus D must be equal to, D itself should be equal to 1, and D is this thing, so this has been proven to be equal to 1. So that is part B. Next, part C. In part C, we have to prove this. Let us write it here. GCD of A and B is given to be 1. We have to prove that GCD of AC and B is equal to the GCD of C and B. Okay, so we will start like this. Let D be the GCD, be defined to be the GCD of C and B. Don't be disturbed by our use of D again and again in different GCDs. It is because once one part is over, it's gone. Okay, then in part B we are starting everything from the beginning. Okay, everything is new. So don't confuse this D with this D, for example. That thing is gone, so the purpose of D is also gone. This is something else. Then D divides C and D divides B, and so D divides AC and D divides B. Because of this, we automatically have this. We have just simply multiplied this by some integer C. Just give me a moment, okay? Okay, so we have got till this. Next, what we do, let K be a positive integer such that K divides AC and K divides B. So K is any positive common divisor of AC and B. Okay, now what we suppose, the GCD of A and K is greater than 1. Okay. We are hoping for a contradiction. So we have supposed that the GCD of A and K is greater than 1, and that the GCD divides both A as well as K. So because that GCD divides A, fine, it divides A, but because this GCD divides K and K divides B, this will also divide B. Now so this becomes a positive, since it's GCD, it's a positive divisor, so it's a positive common divisor of A and B, so it will divide the greatest positive common divisor, which is the GCD of A and B, but that is given in the hypothesis to be 1. This implies and this is a contradiction because a positive integer greater than 1 cannot divide 1. This is a contradiction since so our supposition is wrong, that is we must have this equal to 1. Now you look at this divisibility condition. K divides AC, but K and A are relatively prime. So by a result that we already know, K must divide C. And have I written that here? By which result that follows? So by theorem 2.5, K divides C. So K now divides B as well as C. So K divides both B and C. Okay, let me just see one thing. Where are we going with this? What was our aim? Our aim was to prove that D is the GCD of AC and B. The fact that D is a common divisor of AC and B, that automatically follows from here itself. Next, what we are showing now is that if K is a positive common divisor of AC and B, then K divides D. Yes, okay. We thus have so K must divide the GCD of B and C, which is D. And this in fact is by that alternate definition of GCD, where we don't use the order relation in the set of integers, but we use only divisibility. We have discussed about this before, and we have also discussed a little about how this can be used in algebraic structures which don't have any order relation in them. It's by that theorem, and that theorem is theorem 2.6. So if you are, I think I have not explicitly mentioned it, that here we are using two facts to conclude this last line. We are concluding using that theorem 2.6, that when D is a common divisor of AC and B, where D is positive, and any other positive common divisor of AC and B also divides D, that implies that D is the GCD of AC and B. So in concluding this, we are using theorem 2.6. Hence, this we are not going to mention, I mean, this is the only time we are mentioning it explicitly. And this D is GCD of C and B, so GCD of AC and B and that of C and B are equal. So this is part C. In part D, we have to prove this. As usual, A and B are relatively prime, and now C divides A plus B. Then these things imply that these two greatest common divisors are equal to 1. We can use this hint that is given. So let us start accordingly. Let T be the GCD of A and C. Okay. Then T divides A and T divides C, which imply because C divides A plus B. So combine that with this one and use transitivity of divisibility, you get this. But then or D divides B. Thus D divides A that we have already, and just now we have proved that D divides B, and so D divides their GCD, which is 1. And this conclusion, and so this happens, here we are using that alternate formulation of GCD in theorem 2.6. So D is 1. Hence, D divides 1, hence D is equal to 1. Similarly, one can prove that this GCD is also equal to 1. So that is part D. Then part E. In E, what do we have? In E we have this A and B are again relatively prime, and D divides these two integers AC and BC. Then we have to prove that D divides C. They will start from this, since this is equal to 1, there exist integers x and y such that 1 equals ax plus by. Then multiply by C throughout, ACX plus BCY, and now use these relations. Since D divides AC and D divides BC, we have this. So that's how D divides C, and this is part E. And now we have come to part F finally. Right, so here again A and B are relatively prime. We have to prove that A square and B square are relatively prime. And for this, we will use part C. In part C we had this, A and B are relatively prime, then GCD of AC and B is equal to the GCD of C and B. By part C, we won't exactly write in detail how we are using part C, but I will just simply show it to you. We have this. This is equal to GCD of A and B square. Okay. Oh, okay. No, we cannot write like this. I mean, we are of course going to use part C, but not like this. In two steps we have to do. We have 1 equal to GCD of A square and B. Do you see what we have done here? Think of A in place of C. There is no restriction on this integer C here, so we can take it to be A also. And our hypothesis is true. Now here also that is true. So taking A in place of C gives us A square, and here we get A comma B, so that is equal to 1. So that's how we are getting this. Now using this again we can use part C. So again by part C, 1 is equal to GCD of A square and B square. Now in applying this one, what we did is this. You see, first of all, this function that we are writing is independent of the order in which the elements are appearing, right? So that means GCD of A square comma B square is equal to GCD of B square comma A square, and this is equal to 1 because this is equal to 1. So here what we did, in again applying part C, to conclude this, we have taken C equal to B now. So if you do that, you will get GCD of B square comma A square equal to 1, because GCD of B comma A square is equal to 1. So that just completes the solution. There are 3 more exercises that are left in this set of exercises, which however we will do in the next number theory video, along with the next section that also we will start the Euclidean algorithm for calculating the GCD of 2 given integers. The next section is about that thing. And tomorrow we have our excuse me, exercises from Galilean's algebra, and there we will have 2 videos, both group theory exercises and ring theory exercises. And day after tomorrow is Sunday, when we have analysis. So that's just it for tonight. If you want to say something about this video or anything else, you can write in the comment section below. So I sign up with that. See you tomorrow with Galleon's exercises. Until then, have fun with mathematics. This is me, Lucifer, from a mathematical room. Have a nice night.